About adaptive filters, and I want to get into some of the initial pieces of sort of math and analysis we get with an adaptive filter structure. So we'd start with an adaptive filter which has these inputs and weights, and I'm talking about it for a single output here, which also means an adaptive filter is going to be linear output. It also means I'm going to have target signals, which means I'm going to get an error signal. So this looks very similar to the formulations that you get, particularly from Widrow and so on. And what you find is that this output is going to just be the outer product, or just the inner product of the vector x and vector w. I can flip that in both directions. And now the question is, all right, well, what am I going to get for a learning rule? I'm going to get something that's minus 2xe. Now that 2 comes from the fact that this really is going to be minimizing an energy surface. And so this is a derivative of that form. So great, right? This gives me sort of the derivative, and there has to be a time constant there because I have to figure out how fast is it converging. All right, so now that I do that, I can say, well, here's my terms. I want to try to start pulling apart and figure out what is it solving and how do I begin to think about this analysis. Because here, this defines the entire thing. We could go and implement it. We're good to go. But actually, what does it look like? Well, the first thing you know is that E is going to be related to both y and y hat, and y is then related to x and w. So I can start to build this equation where I had an x here, I have an x vector transpose w, and 2x y hat. Now, the key assumptions here, and usually can never be stated enough when you're looking at adaptive systems. The first one is that your input has to be zero mean. The third one is actually that w has to be of a slow time scale, and x is a fast time scale. And these are typically time scales that are not overlapping. So that way, and in some sense, what you're doing with the slow time scale is you're averaging over enough of the input to make something work. And so this is why these integrals tend to work well. So if I look at t being a period of the fast time scale, so things average out in some nice ways, what I'm going to find is that, if I average that with the x, then I basically just get something to 0. That's what 0 mean is going to be. The slow time scale means if I do that for w, it's going to be w. Now, what's interesting is these also have statistical meaning. So if you're looking at the statistics of this, and the system is ergodic, which means that these moments, these 0, first, second order moments, are basically relatively constant over the space, and I can talk about this as being ergodic. If it is ergodic, then these definitions will hold in terms of the statistical properties. So you would say that x is 0 mean. You'd say that the mean of w over that window is basically going to be the same. And this turns out to be very, very helpful to have these kind of statistical definitions as we work through things. One thing that's very nice is if you look at, we're going to define a matrix Q, because notice XX transpose comes into this and is very important. As a result of it, that Q, is now this integral. Well, that also turns out to be the expected value of XX transpose, assuming things are ergodic. And that really means a covariance matrix, which you could have argued that's true just from this integral, but it has the same statistical properties. And so statistically, I am looking at what is the correlations, as well as what is the signal power, x squared, along the diagonals. I'll also have a second term r, which is then just basically going to be the same sort of thing with x and y hat transpose. And that gives me its core structure. With all of this sort of structure, which is what you need if you're building any adaptive system, you'll always have a multi-time scale problem anytime you do adaptive systems. It just is part of the kind of construction in the approach of this. So with all of this kind of definitions and the definitions of talking about expected values and means and averages, what you end up getting is that I now get this derivative term equals to minus 2q matrix w vector plus 2r. And so I know what the steady state solution is directly. And on top of that, I can now say, okay, if I could solve this, it would do the... But here's what's interesting, right? Because this entire set of this differential equation with this constraint solves this problem for me. But this is actually kind of cool to think about. It goes both ways. So if I do want to do a matrix inversion, I could do that. On the other hand, I could also be running the system and even continuously shift. And if it does turn out that the covariance matrix changes a bit, this can still kind of go with it. And that's a really valuable approach. And so this is huge in terms of being able to get a sense of the system. But there's something further to this, because knowing that this Q is a covariance matrix, I can then start to look at this system a little more analytically in terms of, what are the key properties around Q. One of the first things I know with Q is that it is decomposable, being as a symmetric matrix, into a normalized set of eigenvalues and a diagonal matrix purely of the ordered eigenvalues. And then it's E transpose. This is a symmetric matrix, allows me to use this form. What's wonderful about this is then also it turns out E and E transpose, since they are the eigenvector matrices that have all of the eigenvalues corresponding to all of the particular eigenvalues that I would have in lambda. These are unitary matrices that I can then work with. And these unitary matrices, if I just take the product of the two of them, E transpose or E transpose E, I get the identity matrix. So that's kind of useful that the two of them, the one is the inverse of the other, which is why this E transpose works so well. Great. And so now with the diagonal matrices, by the way, all the eigenvalues are going to be greater than or equal to 0 because it's coming from something real and real signals. So I'm going to be getting something along those lines. I'm going to be getting ordered structures, ordered eigenvectors. Fun thing to happen then is that I can now project W along E and say like W is E times a vector A. And now if I plug this in, I can do that. I can reduce because I can get the E transpose E to drop out. If I just group B equals to E transpose R with this one, I get something that basically just gives me just the change in A, which now is projecting everything on this eigenvector basis. And I can see that this directly is a nice structure where lambda now is diagonal. And so each of these has their own lambda, and there's its own constant. And so now I can actually look at its trajectory and how it converges towards equilibrium. And each of these lambdas matter. And so now this gives me a framework of which I can now solve this. I can now look at various properties. For example, if my lambdas are very, very widely spaced, I'm going to expect that I may have some issues in terms of what's the convergence. Of course, it might also be if the lambda is really small, it's also a very small quantity. So does it matter? Well, that's going to depend a lot on the application. But there's a lot I can very directly ask and a lot of different properties I can directly start to look at in these systems.